Now today we will discuss about another phenomenon that is known as the magnetism. The magnetism uh, and electricity. There is a strong similarity between electricity and magnetism. How we can say both are similar? Suppose if we have two electrically charged rods, they have like and unlike ends. Then, if we bring these two rods together, if they are likely charged, then they will oppose each other. And if they are having unlikely, one end of the rod has likely charge, one end has opposite charge, means unlikely charge. And if we bring these two together, so what will happen? They will attract each other. As we have seen in case of electrical charges, the same kind of charge repel each other, and the different kind of charges attract each other. So there is a strong similarity between these two. Correct. Now, what is the effect of magnetism, and what we can sense from this magnetism? So yesterday we discussed about it. The Michael Faraday, they uh, discovered a fundamental effect of electromagnetism. And what is that? The induction, an ability of wiring magnetic field to induce electric current in a wire. Okay, so the electric current is generated as long as the magnetic field is varying. The varying magnetic field may generate electric current, but if there is no variation, then the differentiation of this magnetic field is zero. So the EMF produced E will be zero, and there will not be any current, because current is the movement of charges per unit time. So that we have seen yesterday. Now, what we can observe from this, if varying magnetic field is applied to a solenoid, solenoid is nothing but a helical type of wire, means a coil. Then the induced voltage we have uh, may be expressed as voltage equals to minus of n d phi b by dt, where phi b is the B is the magnetic field, phi is the flux associated with this field, and n the number of turn coil has. So this equation can also be written as minus n times dBA by dt, because the phi v, the flux, it can also be written as the product of B into A, where B is the magnetic field and A is the area of that circuit. So if an electric current passes through a coil which is situated in close proximity with, suppose we are considering two different coils, okay, one carrying an electric current and nothing is connected to the next coil. So according to Faraday law, what will happen? An EMF will be induced in second coil, okay. uh, and definitely when a coil carries current, it produces a magnetic field that we have seen earlier, we know it. So this magnetic field penetrates the second coil, and not only the second coil, it will penetrate the first coil as well. So what I am saying, if it penetrates the first coil, so that's why a magnetic field that penetrates the first coil sets an EMF in the same coil itself, and this is called the self-induction. The Due to this self-induction, the voltage induced is called the self-induced BMF, and it is given by minus of d and phi b by dt. So, for a simple coil with no magnetic material in the vicinity, this value is proportional to, means n phi b can also be written as L of I, where L is the proportionality constant and I is the current flowing in the coil. So we can write the voltage induced as minus L di by dt as well. And that you know very well. Okay, we can be written as minus L di by dt. So from this equation, we can define the inductance, means the property of the coil material, as minus V by di by dt. means for DC voltage, no induced EMF can be produced. However, there will be some magnetic field associated with that coil. The voltage increases linearly with the current rate of change because of the proportionality relation. Voltage polarity is different, as we know, because this induced EMF opposes the cause that produces it. So we will have negative sign. So the induced voltage is always opposite. Okay, so that's why a negative sign is associated with this. Now, like capacitance, inductance can be calculated from geometrical factors. So, for a closely packed coil, L can be written as N phi V by I. If N is the number of turns per unit length, okay, the number of flux linkage in the length L is N phi V equals to small n into L into BA. So the inductance can be expressed in terms of capital N phi V by I, or it is in terms of permeability, that is mu naught N square L into A. So the L into A is the volume of the solenoid, that is also known as the geometry factor. So thus having the same number of turns and changing the coil geometry, its inductance may be changed. And with this, we can construct uh, an inductive transducer to sense some parameters, some stimulus. So that's why we are discussing this type of the characteristic means this particular type of magnetism. So by sensing the magnetic field, we can design the transducer. That is our aim. Correct. So in this way, another transducer can be designed that senses a particular type of characteristics that is the related to the flux. Okay, magnetism. Correct. So now we come to the conclusion that we have a coil, and the coil can be characterized in terms of its characteristic that is known as the inductance of the coil. So similar to resistance, we have another element. Sorry, similar to capacitance, we have another element. For that, we can say it is having some inductance. So if that type of element is connected into an electronic circuit and some external voltage is applied, so it will provide a complex type of resistance to the circuit, and that resistance can be expressed in terms of the ratio of voltage to current, that is equals to J omega L. But this type of resistance, earlier we have seen the resistance provided by the capacitor was minus 1 J over omega C, and here it is equals to J over omega C. So both are having the complex nature. So these resistances are complex resistors. And the current is sinusoidal. So what happens to this, depending on its nature, means it's complex, it is depending on the frequency as well. So the resistance of the coil can have different values at different frequencies. Okay. So what does it mean from this expression? What we can observe, the complex resistance of inductor increases with the frequency. When frequency is high, its resistance will be more. When it is low, it's less. Okay. So this is the characteristic of a solenoid or a coil. Now, if we have two coils, as I said, one coil in which some electric field is applied, but another coil that lie in the vicinity of one, no field is applied. So what will happen? The coil one, it carries current, so magnetic field is induced in this. It produces some magnetic field, and that magnetic field links with the second coil, means it penetrates the second coil. So if it happens, then it may induce an EMF in the second coil, and that can also be expressed in terms of minus M21 by di1 by dt, where I1 is the current flowing in coil 1, V2 is the EMF induced in coil 2, and n number of turns, as I said, and M is what? The mutual inductance between them. So what is M? Mutual inductance between coil 2 and 1. So M21, what is the mutual coupling that exists between these two coils is represented by a constant, and that is M. Okay. So it can also be expressed in terms of mu pi r n. Okay. So for this, what we can see, what we can observe, if we are able to vary the mutual inductance, we can design a sensor. We can design a useful sensor by varying the mutual inductance. So that is another way by designing a sensor, and that sensor can sense the mutual inductance between these two coils. So, for example, a displacement sensor may have two coils where one coil is stationary and other coil is moving. When it happens, the induced voltage exists or produced, and that may be expressed in terms as V2 equals to this one. And by this voltage, what we can observe, the mutual coupling, and that mutual coupling can be expressed in can be related to the displacement between these two coils. So this type of sensor can also be used to sense the displacement. And how it senses? By sensing the magnetic properties. That is the coupling. Okay. So this is the second sensing principle, means how sensors sense different quantities. So earlier we have seen the electric current, electric voltage, or electricity. Now the magnetic. So based on these, we